This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 2. The first law for closed systems. High yield. 2 or 3 questions lean on this framework. Get the sign conventions right, get the boundary work formula right for the process, and the rest is arithmetic. Here's the problem. 2 kilograms of air in a piston cylinder at 100 kilopascals and 300 Kelvin. Heat is added at constant pressure until temperature reaches 600 Kelvin. Air is an ideal gas with the specific heats given. Find Q, the boundary work W, and the change in internal energy delta U. A classic constant pressure heating problem. Concept. The first law for a closed system is a straight energy balance. Heat in minus work done by the system equals the change in internal energy. Sign convention matters. Heat positive, flowing in. Work positive when the system pushes the piston out. Delta U is final minus initial. Some textbooks flip the work sign, but NCEES and this course use work positive out. The box diagram. Draw this before any algebra. Arrow into the box is positive Q, out is negative. Arrow out is positive W, the system pushing on the surroundings. In is negative. Sketch the box, label the arrows with their signs, then write the first law. Sign errors are the most common way to miss this problem type, and the box eliminates them. Setup. Boundary work is the integral of pressure dV along the path. 4 specializations to know cold. Constant volume, 0. Constant pressure, P times delta V. Isothermal ideal gas, P1 V1 times the natural log of V2 over V1. And polytropic, PV to the n constant, P2 V2 minus P1 V1 all over 1 minus n, for n not equal to 1. N equals 1 recovers isothermal. N equals gamma is isentropic. For an ideal gas, internal energy depends only on temperature. Delta U is m times CV times delta T. Delta H is m times Cp times delta T. 3 identities. Cp minus Cv equals R. Gamma is Cp over Cv. And for air, Cv is about 0.72, Cp about 1, gamma 1.4, R 0.287. For steam or any non-ideal substance, get U from the tables. The Cv formula only holds in the ideal gas limit. Build the variable table. 2 state columns, initial and final, for pressure, temperature, volume, and mass, plus a process column for work, internal energy change, and heat. Mass is the same in both columns for a closed system. Fill givens, get volume from the ideal gas equation, and compute the process quantities last once both states are pinned. Pattern recognition. Rigid tank or constant volume. Work 0. Q equals delta U. Weights holding pressure constant is isobaric. W is P delta V. Isothermal and slow, the log formula. Adiabatic or insulated, Q is 0. W is minus delta U. Reversible and adiabatic together mean isentropic. For an ideal gas, polytropic with N equal to gamma. And heat until set state 2. Handbook quick reference. The first law chapter splits into closed systems, today, and open systems, next topic. A separate ideal gas section holds the Cp, Cv, R, and gamma relations. The first law equation is the same for any fluid. What changes is how you compute delta U, W, and Q. Steam in the dome, use the tables. Air or combustion products, the ideal gas relations. Solve. Step 1. Identify the process and fill givens. Constant pressure, ideal gas. Get V1 and V2 from PV equals MRT. Volume doubles because at constant pressure, doubling the temperature doubles the volume. Delta V is 1.72 cubic meters. Step 2. Boundary work. At constant pressure, W equals P times delta V, 172 kilojoules. Equivalently, W equals mR delta T for an ideal gas. Same answer. Memorize that shortcut. It skips the volume calculation when only work is asked. Step 3. Change in internal energy. For an ideal gas, delta U equals m times Cv times delta T, 430.8 kilojoules. For a delta T, Kelvin or Celsius gives the same value. But for absolute temperatures in PV equals mRT, use Kelvin. Step 4. The first law gives Q directly. Q equals delta U plus W, 603 kilojoules. Free crosscheck. At constant pressure, Q also equals M times Cp times delta T, which lands on exactly 603, because Q equals delta H there. Use it on every constant pressure problem as insurance against sign slips and arithmetic errors. Final answers. Work 172.2 kilojoules. Delta U 430.8. Q 603. All positive. The gas expands, warms up, and receives heat. First law closes. For a rate of heat addition, divide Q by the process time. Same equation with time derivatives. 5 ways this loses points. 1. Don't let sign convention drift. Q minus W equals delta U, W positive out. 2. Absolute temperature in PV equals mRT, Kelvin, not Celsius. For a delta T it doesn't matter, for T itself it does. 3. The highest impact trap delta U for an ideal gas is always CV times delta T. The Cp shortcut is for Q at constant P, not delta U. 4. Match the work formula to the process. Constant V0, constant PP delta V, isothermal log formula, polytropic the PV over 1 minus N. 5. For steam in the dome, delta U comes from the table U column, not CV times delta T. Quick recall. Q minus W equals delta U, W positive out. Memorize the 4 boundary work formulas. Know the ideal gas relations. Delta U uses CV, delta H uses Cp, Cp minus Cv equals R, and the constant pressure shortcut, Q equals mCp delta T. Those 3 pieces handle any closed system problem. Next up, topic 3, the first law for open systems, the steady flow energy equation. Real devices have mass flowing through them, turbines, pumps, compressors, heat exchangers, and we extend the first law to handle them. Very high yield. Before the next video, rework today's problem with the piston locked, constant volume heating. What's Q and the final pressure? PEPrepengine.com/beta. The first law closed system cheat sheet, the worked problem PDF, and a 5-question quiz are attached to this video. If the course helps you, subscribe.
The full study guide with every equation and common exam trap is free at PEPrepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.